Hey, this is Scott. Welcome back to my YouTube channel. Right now we're going through a series on Bayesian statistics and decision making. So this brief video will be about simple example calculations. I hope you join me for Bayes07. That's in my channel and in my playlist specifically on Bayes, where I introduce the intent for the series. So please see that brief 3-minute video. Our agenda today is right here. We're going to review standard conditional probability and Bayes' theorem. Last time we actually did a simple derivation of that, kind of a non-rigorous but explanation of how we derive Bayes' theorem. And then next we're going to get into a simple example of application of that theorem. Did a student study for the test given the test result. Again, this is kind of reverse probability here. And then a simple medical example, the probability of lung cancer given a positive test. So getting straight into it, we derived this theorem last time, Bayes' theorem. The simple case of Bayes for two events, A and B. And we also talked about the fact that the conditions for independent probabilities and marginal probabilities there as well. And you can use Bayes' theorem to determine whether events are independent or not. Okay, so getting right into it, a simple example. Let's suppose that we have this case where the probability that a student passes an exam is 80% if they studied, right? So given that they studied, the probability that they're going to pass is 80%. The probability the student passes exam is 50% if they did not study. All right, so if they didn't study, the probability they pass is 50%. In my class, the probability a student studies is 60%. All right, so the question we're trying to answer is, what is the probability a passing student in my class, Burke's class, actually studied? All right, so let's break this down. So again, we were given that the probability of student studies is 80%, or I'm sorry, passes the exam is 80% given that they studied. B is the event that they pass. A is the event whether they studied. So mathematically, we can post this as probability of B given A is equal to 0.8, right? This is B given A is 80%. The probability student passes the exam is 50% given they did not study. The way we denote that is this is the probability of B that they passed given that they did not study. In other words, the complement of A complement. So that's 50%. In my class, the probability of student studies is 60%. So that's just a simple probability of A, and that is 60%. And then this is what we want to know. What is the probability a passing student in Burke's class actually studied? All right, so, and again, we're trying to answer this question: did the student study given the test result? All right, so this is just kind of a repeat from before, just so that we can see it all together. Probability of B given A, 0.8. Probability of B given not A, or A complement, is 0.5. The probability of A is 0.6. And then here is mathematically what we want to come up with. We just substitute in, right, the 0.8 right here, right? This right here is this right here, up here. And then the 60% is this probability of A. And then for simple case, this is the exact same thing that we have on top. And then we just have to add the complements, right? So we said that the probability of B given not A or A complement is 50% times the probability of not A, which is 1 minus this, which is 0.4. Plug all that in, and the answer is 70%. 0.6%. So that is the probability that the student passes. I'm sorry, the probability that the student studied given that they passed in my class. All right. And let's look at one other quick example. This is a lung cancer example. Probability a patient with lung cancer has a positive test is 98%. So the probability of positive test result given that they have lung cancer is 98%. All right, that's traditionally what we do, right? We look at the probability of a positive test given that this individual has lung cancer. All right, A is the event of lung cancer, B is the event of a positive test. So the probability a patient without lung cancer has a positive test result is 5%, so that's 0.05, right? And then the percent in the general population with lung cancer, there's only 1% in the general population of people that actually have lung cancer. So here, the probability what we want to do is what's the probability of lung cancer given a positive test result? That's this right here, probability of A given B. And again, using Bayes formula, this is what it boils down to. So we already said that the probability of B given A is 0.98. And the probability of having lung cancer in the general population is 1%. So the numerator here is 0.0098. And then the denominator essentially is that same thing plus B given A complement, which is 0.05 times 0.99 or 0.0593. Okay, if we want to flip back, we can flip back and see just where those are. This is the 5% that we were just looking at on this slide right here. And the 99% is just 1 minus this 0.01. All right. So that means the probability of having lung cancer given a positive test is only 16.5%. Now think about that. The probability that you actually have lung cancer given that you have a positive test is 16.5%. Most people don't understand this at all. What they think is that this is the outcome. Probability of lung cancer with a positive test is 16.5. Probability of no lung cancer with a positive test is 83.5%. And so most people think that the test is 98% accurate. All right, I'm going to flip back here a couple slides. Where did that 98% come from? Right here. The probability of a positive test given lung cancer is 98%, but that doesn't mean that it's very different than what we have here, the probability of lung cancer with a positive test. And that's where we just really don't understand. The general population doesn't understand what's going on here. So the probability of lung cancer given negative test results, and this is the negative result, right? So we take that complement, right? And we multiply this out. You have all the figures. This is, you can consider this homework. Match this up. Because I've given you all of the numbers. You just need to basically calculate the complements here. And hopefully by the time you get that, the probability of lung cancer given a negative test result is 0.02%. Now that's pretty good, right? I mean, that's pretty good. The probability of lung cancer is very low given you have a negative test result. So that part of the test is good, but yeah, the other is not. So, Anyway, just a summary here. Most people don't understand the accuracy of medical test results. Even with extremely high accuracy of identifying positive result doesn't ensure true positives, and many false positives are likely to exist. So this is what I always say. Statistics is not about statistics is about quantifying your uncertainty, right? What the uncertainty numbers are. We don't eliminate uncertainty. That's not, we can't do that. That's impossible. And if you know much about hypothesis testing and everything, yeah, there's different types of errors, and there's no way of eliminating those errors. So, in fact, nothing can eliminate uncertainty except maybe delusion. So with that, I will let you go. I'll pick back up next time with Bayes08. I'm doing a full series. You can find this in the playlist. You can find me on YouTube, just Scott Burke, my name, and then type in Bayesian or find that Bayesian playlist that I have out there, or check out my other videos or some of the books that we've written. Thank you.